I will use a very simple system. Carbon dioxide, 2 oxygen molecules, carbon molecule in the middle, aligned on a line, that's called collinear, and we'll only consider the classical version of that system in which these 3 bodies are connected by 2 springs, by 2 harmonic potentials. And we will find the vibrational eigenmodes of that system to illustrate the power of thinking in terms of eigenvalues and eigenmodes and eigenfunction and eigenvectors, 1. But number 2, I will use this to sneak in a very important concept that shapes almost all of modern theoretical physics, and that's the concept of symmetry. My message will be very simple, and it'll be repeated 10 times this semester. If you have a symmetry, use it. Consider a situation in which our physical problem is defined by a Hamiltonian function. What is a Hamiltonian function? That's an operation that you apply on the state of the system and returns a number which is called energy of the system. So that's the meaning of Hamiltonian function. It's an amazing thing because it takes many dimensions, returns one number energy. But if you vary this function, you get equations of motions, which are a high dimensional set of things. And assume that there is another matrix, a very simple one. For example, you permute several directions in the space, which you used to call X, you call Y, or you reverse the direction in which you move. So that's a simple matrix. The system has a symmetry. That means that the energy of the system measured once I've changed these coordinates around is still the same energy. That means that I can first measure the energy, then permute coordinates, or I can first permute the coordinates, measure the energies, and I get the same result. That's an example of a symmetry. During this course, I'll define it in 2 or 3 more ways, but that's one way to understand symmetry. If you have 2 operations with the system, the symmetry operation and the measurement observable operation, and if they commute, we say this system has a symmetry. Next, we use spectral decomposition. Anytime we have a matrix, it has its own Hamilton-Cayley equation, which I write in a form of. And the main thing about spectral decomposition is that we can use the projection operators to replace the evaluation of the matrix on a high dimensional space by the sum of ordinary scalar numbers or the eigenvalues. And if you take any matrix function, we can evaluate it as a set of ordinary one-dimensional functions returning one-dimensional number, 1 per each subspace. And we can use that to decompose the Hamiltonian into sum of Hamiltonians acting on the subspaces defined by these projection operators. And you can visualize this by saying the original Hamiltonian was a big matrix, this guy here, but now we write it as a sum of blocks where it's a small matrix in a first block corresponding to the first eigenvalue of this other matrix M. Second block, the eigenvalues of the simple matrix, let's say symmetry matrix M, block diagonalize the big thing. So instead of having calculations with d square elements, we have a smaller calculation in each block.